So now that you know a lot about Java thread interrupts, let's compare and contrast Java thread interrupts with other types of interrupts you might be familiar with from other courses, such as a computer system organization course or an operating system course. So we'll compare and contrast Java thread interrupts with hardware and operating system interrupts. And as you'll see, there's some very, very significant differences between these different types of interrupts. So interrupts that occur at the hardware or operating system layers typically have several key properties. First and foremost, they're almost always asynchronous, which means they can occur essentially anytime and are independent of the current instruction and its execution context. So if an instruction is running and an interrupt occurs at the hardware or OS level, typically that will interrupt a running instruction, and an interrupt handler will be called to handle that exception somehow. Something else to note is that programs typically don't need to test for these exceptions explicitly, or these interrupts explicitly, since they occur out of band, and we'll see what it means to be out of band in a moment. The other property, which is really part and parcel of out of band, is that these types of exceptions are preemptive. They will intrinsically or inherently pause and then later transparently, hopefully transparently resume the execution of the currently running code or the currently running instruction or the currently running call without requiring any cooperation whatsoever on the part of the code that's being interrupted. Here's a very simple example that illustrates this. This is an example from Unix system programming and its handling of the SIGINT signal, which is the interrupt signal. So as you can see here, SIG interrupt is generated asynchronously. So this particular program is going to go ahead and register the SIGINT signal, and then it's going to go into a loop where it's going to sleep basically for 10 seconds and do this forever. And if while this program is running, Control-C is typed on the terminal or the console, that will cause the SIG handler function to automatically be called back by the underlying runtime of the operating system. And in this case, it's just going to print out receive SIGINT. And that will basically preempt the current call and then handle the interrupt. You don't have to test for this explicitly, you just do it. And it goes ahead and runs and will print this value out. Now, these mechanisms, asynchronous and preemptive interrupt handling, are very, very powerful. They're very important when you program an operating system kernel in order to make it responsive without having to have a lot of thread contexts and threads running around and doing things entirely in a threaded manner. So they work very well, they're very scalable, but they're complicated, they're tedious, they're error prone, and they make it hard to reason about the behavior of the program. And that's because race conditions can occur in all kinds of situations where things are happening in interrupt handlers that you're not expecting to be called. There's various things called reentrancy problems, which means if you have a function that uses some kind of static data or shared data that's not properly protected, then if it gets interrupted in the middle of its execution and something happens that changes the state in a way that when it resumes, it's no longer in the state it was in before, that'll cause all kinds of problems. A good example of this, for example, would be memory allocation. If you're running a program that's doing memory allocation and an asynchronous preemptive interrupt occurs, then if in the interrupt handler you do something else that requires dynamic memory allocation, like call free or call new or delete or malloc or whatever, in that case, that can corrupt the data structure that was being worked on before the interrupt occurred. Yet another thing that often happens is some system calls are called slow system calls that cannot be transparently restarted. So a good example would be an IO operation that gets interrupted. It may return, and you may have to go ahead and restart the operation if you want to have all the bytes read. And you can read more about these kinds of problems in the links at the bottom of the slides. In contrast to the operating system and hardware interrupts, Java thread interrupts differ in a couple of key ways. First and foremost, delivery is synchronous and non-preemptive rather than asynchronous and preemptive. And in particular, what that means is that these interrupts don't occur at some arbitrary point, and they don't pause and later resume the running code transparently. All that stuff has to be done voluntarily. And so as a consequence of this, a program has to test for these interrupts explicitly, as we've seen with things like our volatile flags or our thread is interrupted or thread interrupted methods that can be called back to test whether the interrupt status flag has been set. Typically, in that case, we handle these things by throwing interrupted exceptions, but those are thrown synchronously and they're handled synchronously. They're not thrown asynchronously and they're not handled asynchronously. They're thrown and handled synchronously. Moreover, certain operations just cannot be interrupted in Java, which is a blessing and a curse. For example, blocking I/O calls that aren't invoked on so-called interruptible channels. For example, this code here where you block waiting for input to come in from the console, you can't interrupt this thing. It's really frustrating. It's a bug that's been in Java for who knows how long, but they've never fixed it. Likewise, as we've talked about several times before, if you're a thread and you're waiting to acquire an intrinsic lock in a synchronized method or a synchronized statement, those threads and that waiting to get that lock cannot be interrupted. Of course, once you've got the lock, then the thread can be interrupted. But while you're waiting for the lock, you can't be interrupted. So that's a quick overview of the differences between hardware and operating system interrupts and Java thread interrupts. As a general rule of thumb, the Java thread interrupts are a lot more civilized, but they're also a little bit less responsive and less efficient as well.